Example 3, we've been given another piecewise function. So we have the left-hand side of that piecewise function as x squared, and we have the right-hand side as the linear function 6x minus 9. And at x equals 3, f of x is undefined, differentiable but not continuous, continuous but not differentiable, neither continuous nor differentiable, or both continuous and differentiable. Okay, so what we want to do first of all is check for continuity and see if it's, first of all, check to see if it's defined. Well, in this case, it is defined because of that, it does include the boundary 3 on the 6x minus 9. So that's okay. So it is defined. So I'm just going to get rid of that to start. So we get rid of that one. And for B, continuous but not differentiable. Okay, so we should probably check for continuity first. So let's check for continuity. And for checking for continuity, we're just going to check the limit, the left-hand limit, equaling the right-hand limit, and checking to see that it actually equals. So equals the value. So limit as x approaches 3 from the negative side of x squared. That's equal to 9. On the right side, the limit as x approaches 3 from the positive side of 6x minus 9. That's going to be 18 minus 9, which is 9. So it matches, and the value at 3, so f of 3 is also equal to 9 because we're just plugging in 3 into the 6x minus 9. So we know that it has a limit at x equals 3, and that limit equals a value at 3, so we know that this is continuous. Okay, so we know it's continuous, so we can eliminate some more of these possibilities. So it says neither continuous nor differentiable. Okay, well that's not true anymore because we know that it is for sure continuous. Okay, let me just do that one more time. So we're going to get rid of that example there. Okay, so neither continuous nor differentiable, it is continuous. Okay, so we're going to now check for differentiability. So we need to check the f prime value. So I'm just going to find the f prime. So differentiating this, I get f prime of x. That's going to be equal to 2x from the left side. And it's going to be equal to 6 from the right side. Okay, so we're going to check then the derivative from left and right hand side. So the limit as x approaches 3 from the negative side of 2x, that's going to be equal to 6. We're going to check the limit as x approaches 3 from the positive side of 6. Well, that's just going to be 6. So we know that the left-sided limit and the right-sided limit are the same, and we know that it equals 6 at that point. So we know that this is continuous for the derivative, so it must be differentiable. So we know that this is both continuous and differentiable. So getting rid of a few more of these. Differentiable, but not continuous. We already just established it's continuous. We established it is differentiable, so we can get rid of that one. And then, so we know that the answer must be both continuous and differentiable, so the answer is going to be E. Okay? For example 4, it says, if A is not equal to 0, then the limit is, well, we're going to first of all try to evaluate the limit as x equals a. So as x goes to a, plugging it in, I'm going to get a squared minus a squared over a4 minus a4. That's going to give us 0 over 0. So this is an indeterminate form, but this is good because now we can apply L'Hopital's. So applying L'Hopital's to this, we just have to be careful because when we apply L'Hopital's to this, we have to remember that a to the power 4 is not a function. a to the power 4 and a squared is a constant. So when we differentiate this, we're just going to differentiate the x. The a squared differentiates to 0. This becomes 4x cubed. A4 differentiates to 0. We can simplify that expression. And so we end up with the limit as x approaches a. And this is going to be just going to be 1 over 2x squared when we simplify it. So then the limit works out to be 1 over, plugging in the a, 1 over 2a squared. So there's my solution for that problem. So the limit of x squared minus a squared over x4 minus a4 as x goes to a, the limit is 1 over 2a squared. For example 5 then, we have this limit of an integral. Okay, so first thing is I'm just going to evaluate this limit to see where I'm at. So the limit as x goes to 1, so that's the integral or the area under the function et squared from 1 to 1. Well, if the area is from 1 to 1, I'm just going to write that out, 1 to 1, under any integral, that area is going to be equal to 0. Okay, so that's going to be 0. So we have that, the numerator, when I plugged 1 into the denominator, 1 squared minus 1 is equal to 0. Okay, so that's fine. I now have the conditions for L'Hopital's. Now, I have an integral expression in the numerator though, and I need to differentiate that expression. So when I differentiate that integral, I'm using the fundamental theorem calculus that the derivative and integral will undo each other. And I put a note over here, and this is separate from this work here. Okay, so if we can justify this because if we differentiate f of x, first of all, if we integrate f of x from a to x, we're going to have f of x, big F of x minus big F of a. And differentiating that, we're going to have the derivative of big F and the derivative of f of a. Well, the derivative of f of a becomes 0. The derivative of big F becomes small f. So this will then, we can see how the integral and derivative kind of undo each other. Okay, so we don't need to show that part, but that's why it works. So I do have the conditions for L'Hopital's, so I'm going to apply L'Hopital's, which means I'm going to differentiate that integral. So I get the limit as x approaches 1. The denominator is going to just be 2x. The numerator is going to be that expression. Now, I can't integrate that expression and then differentiate it, but I don't need to because I'm going to apply the fundamental theorem of calculus and just say that the derivative of that integral, maybe I'll just write that out, d by dx of the integral from 1 to x of et squared dt. When I differentiate that, I'm just going to end up with the expression that I had in here. Okay, so I get the limit as x approaches 1, and that's going to just end up being x squared. And I end up with 2x in the denominator. Well, I can evaluate that limit. When I put 1 into x, I'm going to get e to the 1 in the numerator. In the denominator, I'm just going to get 2 times 1, which is 2. So this represents the limit of that expression as x goes to 1.